So far we've been talking about these photodiodes, which is actually the front end of the optical receiver, and we understand now that you have light incident on this photodiode, and the photodiode generates a certain photocurrent. It could be a PIN or a APD photodiode, but it generates a certain photocurrent. Now we discussed before in terms of the overall optical receiver design, we need to convert that photocurrent into a corresponding change in voltage, right? So what are the kind of circuits that you would want to consider for something like that? Okay, that's what we want to look at next. Okay, so one simple configuration is what you would call as a let me just use a different color, direct load configuration. And in a direct load configuration, what we have is this photodiode, right, which is going to generate the photocurrent upon certain light that's incident on it. This could be grounded, or it could be with some bias as well. But this photocurrent that's generated, IP, which is actually a function of T, now that is going to that external circuit, and then you typically have in this configuration a resistor, right, of value, let's say RL, and then you are looking at the output between the potential difference between this point and ground, so that should correspond to IP times RL, right? So that's what you get at the output. Now what really is happening over here? Well, the photocurrent actually flows through this resistor, and so there is actually a potential difference, which is what you are trying to pick out over here. But in doing so, one thing that happens is this potential that develops here is going to act against the potential difference across the diode, or in other words, if you let's say you have a certain bias over here, certain reverse bias. Now this potential difference is going to work against that reverse bias, and that might end up limiting the current. The best way to look at what's happening there is by looking at the IV characteristics of the photodiode, especially under this loaded condition. Okay, so let's go back, and I'm sure you have seen this before. IV characteristics of any photodiode, any diode for that matter. So this is I and this is V, and use a different color here. So on the reverse bias case, it goes here beyond a certain point, it goes to breakdown, but it goes as an exponential under forward bias. So the question is, what happens if you have light incident on it? If without any light incident on it, if you change the voltage across the diode, this is what you get to see as far as the current is concerned. But what if there is some light that incident on it? If there is light incident on it, then what we will find is that correspondingly there will be a change in the photocurrent, basically the reverse current that you're getting off the photodiode, and so you would have an increase like this, and then like this, and so on, right? So you'll have a corresponding increase like this, and this is actually as a function of increasing intensity, or the power that's falling on the that's incident on the photodiode. Now me just see if I can take this out, because I want to write something else there. Ideally, what you want across this is something like this. You want what is called a load line. In the ideal case should be something like this. As you increase the intensity, you should be able to get a corresponding increase in the photocurrent. Okay, so in other words, if we were to look at this photocurrent as a function of Pn, in the ideal case it should be like this. It should increase with the incoming optical power. But what is happening in this direct load? Now, as we talked about, because of the photocurrent that's going through this resistor, you have a potential difference here, and that potential is acting against the potential that the diode is experiencing, which could be a reverse potential. Okay, so effectively the load line now is not the same as what we have over here. Instead, the load line goes something like this, right? And maybe just to reduce the confusion, I should remove this part here and say this is actually the load line for a direct load configuration, meaning as this current goes in, and then it is setting up a potential here that is effectively reducing the potential, and in that process it's also limiting the current. So the current should be over here, but because of this potential that is developed, the current is actually lower. So it's actually limiting the current. Okay, so because of this load line, now what we are saying is your current is going to be limited. Okay, so this is what happens in a direct load configuration. Okay, so direct load configurations are not very good if you want to actually extract the most amount of current from your photodiode corresponding to the amount of light that's incident on that photodiode. Okay, so what is the way out? What can we do to get around it? Well, you have a configuration based on an operational amplifier. Okay, and this is actually a configuration that's called a impedance amplifier. So what is the configuration for a transimpedance amplifier? Well, we have the same configuration here as far as the photodiode is concerned. Maybe it's grounded or maybe it's biased, but then there is a photocurrent that's generated. Now this is actually connected to an op amp. Okay, with the other input of the op amp maybe at ground. So you connect to the negative of the op amp because what we will see further down is actually this is corresponding to a feedback circuit over here. So if you have positive, if you connect it to the positive, there is a possibility of the circuit becoming unstable, and then it can basically become an oscillator, right, with positive feedback. So we typically prefer the negative feedback configuration for something like this. And if you have in this case IP that's generated because of light that's incident on this photodiode, the properties of the op amp actually comes into the picture. So, what are the properties of the op amp? Well, for an ideal op amp, one property is that it does not allow any current to flow into the terminals. Okay. So, an ideal op amp does not allow current flow into its input terminals. Okay, so that is one property, and by that what we are saying is, okay, the current cannot flow here, so it has to flow in the feedback circuit, where you have you might have a certain resistor RF. Okay, the other property of an ideal op amp is that when you look at the potential difference between the two input terminals, the potential difference has to be 0. Potential difference, let me see if I can make myself some room. Potential difference across input terminals is 0. Okay. So, what does that mean? Well, you do, because of the current flow over here, the current is actually, if it cannot go here, it goes through the feedback circuit. So, there is a potential that's generated over here. Now, this is virtual ground. So, there is a potential difference between these two. So, what does the op amp do? Well, the op amp essentially sources a current from its output, and essentially it tries to negate that potential, okay, with the effect that when you look at the output voltage across the op amp across this point, that will correspond to minus of RF multiplied by IP. Okay, it's minus because it's actually connected to the negative feedback terminal. Okay, so you get an output correspond to minus RF multiplied by IP. Okay, so how is this different from this case, from the direct load case? Well, in direct load, we see that the load line is actually slanted, which means that it limits the current that you can extract out of it, whereas as far as this transimpedance amplifier is concerned, there is no such restriction. Okay, I will say there is no such restriction, but I would also say that eventually there is a restriction, because there is only so much current that this op amp can provide, okay, to negate this or to nullify the potential difference at the inputs. And so it cannot, I mean, the op amp is rated for a certain output current, so it cannot provide any more current than that. Okay, but that's a non-ideal condition, right? So until that happens, you are able to extract the photocurrent. So that typically happens for an op amp in the order of tens of milliamps. So you are typically fine with that. So effectively, what we are saying is the load line for a transimpedance amplifier is going to be closer to this ideal condition. So an op amp would essentially behave like this, right, in terms of the current that's extracted for the amount of power that's incident on the photodiode. Like I said, it will probably saturate over here because of the limitation in terms of the current that the op amp can supply. Now, that's a secondary thing. Overall, this is actually a much better configuration, the transimpedance amplifier. if you are interested in extracting as much photocurrent as possible from your photodiode. Okay, and that's one of the more common configurations that's used. In reality, this is all that we have talked about is actually the DC characteristics. When you're talking about AC characteristics, you are interested in the frequency response of your circuit. You have to also consider certain feedback capacitance also here, CF, which could be some spurious, some parasitic capacitance that you incur in your board, or this resistor value itself can exhibit certain capacitance. So you have essentially a RC circuit in the feedback. Because of that, when you look at the overall response of this, the response would correspond to 1 plus j omega RF CF. The frequency response in as far as the AC condition is concerned will be given by this. So what that tells you is that this amplifier is going to be providing this gain only up to a certain frequency, okay, a certain frequency wherein this frequency comes in this omega, right? Omega is 2 pi f, okay. If f is much greater than 1 over RF CF, sorry, if f is much lesser than 1 over RF CF, then this entire component will be very small, so it may be neglected. So at low frequencies it may be neglected, but as you increase your frequency, as you approach that 1 over RF CF value, you're going to have essentially the amplification getting reduced. So the frequency response is going to be poorer as you go to higher frequencies. Okay, so there is a limitation in terms of the bandwidth that you can achieve based on this configuration. So that's one of the downside as far as a transimpedance amplifier is concerned. We didn't talk about it explicitly, but even if you go back to this, you would basically say that this photodiode has got certain capacitance. So that capacitance in parallel with this RL, that also provides you a sort of bandwidth constraint as far as the response is concerned. So that's not anything different, as far as compared to this what's happening with this transimpedance amplifier case. However, there is something else that's happening in a transimpedance amplifier which further sort of constricts the bandwidth. So what is that? So let's look at this in a little more detail. Now when we look at the frequency response of this op amp itself, so what is called the open loop response of the open loop gain of the op amp as a function of frequency, that typically it's like this, it's relatively flat at low frequencies, but then it starts going down as you go to higher frequencies, because there's a certain gain bandwidth product which is actually limiting the gain that you can achieve from the op amp, which is essentially saying that if you go to higher and higher frequencies, the gain that you can extract from the op amp is going to be lower, and this is going to be given by what is called this gain bandwidth divided by whatever is the limiting frequency that you want to apply over here. So the limiting frequency that we are typically interested in is the 3 dB frequency, where the response of the receiver goes down by a factor of 2. Okay, that's called the 3 dB frequency. Okay, so f limit could be the 3 dB frequency. But if you for any of these op amps, if you are looking at the expression for the f limit based on what we looked at here, based on the frequency response over here, you can write the f limit as you have this a limit, the open loop gain at that particular frequency, divided by 2 pi RF CF. But you could also have other terms. You could have a term corresponding to the diode itself, right? If you just go back and look at this capacitance across the photodiode, that's actually in parallel to CF, okay? And also there is a capacitance corresponding to the op amp, the input of the op amp, okay? So that is also parallel to CF. So you can have multiple terms over here. So basically say CF plus CD plus COA, and you could maybe even add other parasitic capacitance because of the traces in your PCB, in your printed circuit board. Okay, so that's actually the expression for the f limit. But what we are interested in is actually, but we also know that your a limit is given by gain bandwidth divided by f limit, and you can choose that f limit to be corresponding to your 3 dB frequency, in which case what we are saying is, if this is gain bandwidth divided by f can be taken over there, so that becomes f square is equal to gain bandwidth divided by this value, or f 3 dB can be written as square root of gain bandwidth of the op amp divided by 2 pi RF CF plus CD plus C op amp and so on, right? So effectively your 3 dB bandwidth is going to be limited by the gain bandwidth of your op amp, and of course you also have a limitation with respect to the RF and CF CD. So you try to keep these capacitance values as small as possible, okay? And for example, you pick an op amp whose input capacitance is a much lower value compared to these two, so you can neglect this and you can consider these, and you can keep the feedback capacitance, the parasitic capacitance and all that to about 0.5 picofarad. Let's say you can actually reduce the diode capacitance by having a larger bias around the diode, across the diode, right? So as you increase your reverse bias voltage, you would typically find that this capacitance, the ability to store charges within that diode actually reduces as you go to larger reverse bias. Okay, so the capacitance value could be reduced because of that. So let's actually look at some realistic values for these all these different things. Now consider say a popular op amp is OPA 656, which has a gain bandwidth product of roughly 400 megahertz, it's one of the op amps with higher gain gain bandwidth product. Typically it's much lower than that. If we pick let's say like our example over here, we want a transimpedance gain of 1 megohm. So let's say RF is 1 megohm, okay, and CF equal to CD equals to, let's say it's 0.5 picofarad, okay. So if you plug all of these values into this, so this is actually 1 picofarad, so that's about 10 power minus 12. This is RF is 1 mega ohm, so that's 10 power 6. So you have a 2 pi term, and then you have a 10 power minus 6 over here, and the gain bandwidth is 400 megahertz. So 4 into 10 power 8. So there is a 10 power minus 6 over there, so that can go at the top. So that becomes 10 power 14. So you have 4 by 2, so that's 2 by pi, which is roughly about 0.6 or so, so it's about 0.7. So if you do all that calculation, you'll probably find that this would imply that F3 dB is equal to roughly about 8 megahertz. Okay, so what does that tell you? If you want to actually achieve this 1 megohm transimpedance gain, your frequency response is going to be limited to 8 megahertz. If you want to have a higher frequency response, so for example, if you are using a distributed sensor where you need say a frequency response of 50 megahertz or maybe even 100 megahertz, what you're going to have to do is you will have to drop this value, right? Because your op amp is whatever it is, you picked up one of the best op amps that's available in the market, which is the highest gain bandwidth products that you have. So you don't have a choice. You cannot get rid of these. So you will have to drop your RF accordingly. Okay. So if you have 3 dB has to be 10 times more, RF has to be dropped by a factor of 100 because it's actually coming into the root, right? So then you ask the question, if you go back to this application, I want 1 megohm transimpedance gain. I can get only 10 kilo ohm transimpedance gain from this stage. So I need a further 100 to get this overall gain. So then I would have to put a voltage amplifier, okay, beyond that to give me a gain of. So what we are saying is, if this is let's say this is 10 power 6, then sorry, so this is not 10 power 6, this is so what we talked about is 10 power 4, right, is the if you want to achieve 80 megahertz bandwidth, then this has to be limited to 10 power 4. So then you will have to limit this to 100. Okay. In practice, you will find that some of these capacitance values are not so low. The op amp capacitance also not negligible. So you will struggle to get even this value. It's going to be lower than that because of all these parasitic capacitances and all. But that's a game you're going to have to play. So you essentially have these op amp based transimpedance amplifiers where we once again play a trade-off between the maximum gain that you want to achieve from the transimpedance amplifier versus the bandwidth that you want to maintain in doing so. Okay. So we will look at further issues. So what we want to now, so I think we are nicely set up now that we have covered the front end photodiode as well as the transimpedance amplifier section. So, now we can actually go into noise issues and then see how noise plays a role in the design of such circuits.